Okay, so the question that I had the most problem with was this one. It has to do with a very thin plastic rod that has a length of L and is rubbed with a cloth and gets a negative Q charge. So here's the first part of the question. We have to determine the electric field dE from the arbitrary piece of the rod from this location right here. That's a distance d to the right and a distance h above. So I've actually done the work already, and I will go step by step on how to accomplish the answer. And I've actually already drawn the diagram over here. So the first step is to recognize that the electric field is equal to 1 over 4 pi epsilon, which we already know is 9 times 10 to the 9. I'm about to make an arrow. Times q divided by the magnitude of r squared times r hat. Okay, in order to find r hat, we first have to establish what our observation location is. That is 0, h, 0. And then we have to establish what our source location is. That's negative x, 0, 0. Then to find r hat, we have to do observed minus the source, giving us x, h, 0. You basically subtract these from each other. And then to find the magnitude of r, you take the square root of each part of r hat to get x squared plus h squared. And then you divide the coordinates you had originally got by the magnitude right here. And that's your overall r hat right here. Okay? And now, since it's asking for dE of the electric field, the derivative of the electric field, the only variable that changes is the charge. So this is a constant. 9 times 10 to the 9th is a constant. Okay? So something that we're also missing is dq. In order to find that, we apply this concept right here. This concept is rho is equal to the charge divided by the length. We were given that it has a uniform negative q charge, so that's why there's a negative sign right there. So it'd be negative q divided by L. And then since we're trying to find dq, it'd be dq equals rho dx. So, thus giving us dq equals negative q over L dx. Now, it's just a matter of plugging everything in correctly. We have dq, we have r hat, and we have the magnitude. So once you plug all that in, here's the dq, and then this entire portion right here is r hat, and then this portion is our magnitude squared, right there. That is what everything is. And then this is our constant, 9 times 10 to the 9. And now, in order to get it more simplified, since we know that this is technically raised to the 1 power, it'd be 2 over 2. And this is actually also x squared plus h squared to the 1/2. So as you know, when you multiply two exponential factors, you're technically adding them, thus giving us 3/2 in the denominator. So it'd be dE, the derivative of the electric field, is equal to this constant times negative q over L, which was our dq, times these coordinates, which is our r hat, divided by x squared plus h squared to the 3/2 dx. Dx is our integrating factor. Okay? And that's all there is to it for part A. And now for part B. Here's the question. Pretty much, once you figured out part A, you just convert dE into an integral, and you solve it. Like, you don't really have to, actually you don't have to solve the integral, you just have to figure out what the integration variable is and what the limits are of the integration. So in order to do that, this is what you have to do. So as you can see, originally we had this, and now you want to get to this. So you take the integral of dE, and as I had mentioned earlier, this is all a constant. These are constants. So you can't integrate a constant, really, so you just take them out of the integral. And what stays in the integral is the coordinates that we had established earlier, and the x squared plus a squared to the 3/2. And here's our integrating factor, dx is our integrating factor. Okay, and our limits are L plus D to D. L plus D, if you look at the diagram again, is the entire distance of this rod plus this portion. And then to D, which is just this portion. The reason why we're only doing it for that is because of what we had mentioned, what the question had asked earlier. And also taking into consideration the location of the observation location. So the charge is obviously spread over the entire length of L, that's why we have L, but then you have to also take into consideration this distance plus D, which is the distance away that the observation location is. And then the upper limit is D, only D, because that's the distance that the observation location is by itself, without taking into consideration of the charge. And this is how you do problem 4 on exam 1.